Welcome to the sixth session of this polynomial series. In this video, complex zero and its modulus will be applied in solving polynomial questions. We will demonstrate you in detail how to apply the complex zero in combination with the formulas of the relations between polynomial zeros and its coefficients through three worked examples.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome back to the series of polynomial, and this is the sixth session of this topic. In this session, we are going to continue to focus on the questions regarding polynomial zeros and conjugated roots. The first example shows a polynomial function px n minus 1, or in parentheses multiplies x raised to the power n minus n times x raised to the power of n minus 1 plus 1, where n is an odd integer greater than or equal to 3. There are 5 questions about this polynomial. The first question is to show that the polynomial px has exactly 2 stationary points. The second question is to show that the polynomial px has a double zero at x equals 1. The third question is to draw the graph of the polynomial px, and based on that, to explain why px has exactly one real zero other than 1. The next question is to show the value of alpha is greater than -1 and is less than or equal to -half, given that alpha is a real zero other than 1. The last question is to deduce that each of the zeros of the polynomial x raised to the power of 5 minus 5 times x raised to 4 plus 1 has the modulus less than or equal to 1. As for the first question, it asks us to show that the polynomial px has exactly 2 stationary points. We need to look at its derivative function. So p prime x equals n times n minus 1 in parentheses times x raised to the power of n minus 1 minus n times n minus 1 in parentheses times x to the power of n minus 2. After factorizing, we set the derivative function of p prime x to 0 and then find the polynomial px has 2 stationary points at x equals 0 and 1. Here we continue with question 2 of example 1. In order to find a double zero, we replace the variable x by 1 in the polynomial px as well as its derivative function p prime x. We find the results of both p1 and the p prime 1 are equal to 0. Therefore, px has a double zero at x equals 1. Since n is an odd integer and the polynomial px has a double zero at x equals 1, so when n is greater than 3, according to the complex conjugate root theorem, px has 3 real zeros and n minus 3 numbers of complex zeros. Apart from a real double zero at x equals 1, there is another real zero other than 1. However, when n equals 3, px has 3 real zeros. The graph of polynomial px versus x has been plotted at the values of n equals 3, 5, 7, 9, and 11 respectively, in which we can see that the polynomial has a common double zeros at x equals 1. Apart from that, it also has a zero between somewhere from -1 to -half. We will find out this later. Here we continue with question 4 of example 1. In order to prove that the other real zero is between -1 and -half, including the point of -half, we need to prove that p -1 is less than 0, while p -half is greater than or equal to 0. If n equals 3, px equals 2x cubed minus 3x squared plus 1. After being factorized, it equals x minus 1, or in parentheses squared, multiplies 2x plus 1, or in parentheses. So, apart from the double zero at x equals 1, there's another zero, alpha, which equals -half. When n is greater than 3, p -1 equals 2 minus 2n, which is obviously less than 0. After being simplified, p -half equals 2 raised to the n plus 1 minus 3n, or divided by 2 raised to the n. Since 2 to the n plus 1 is greater than 3n when n is greater than 3, p -half is greater than 0. According to the above, the other real zero, alpha, falls in between -1 and -half. When n equals 3, alpha equals -half. Here we continue with question 5 of example 1. Since n equals 5, there are 5 zeros for this polynomial. Px now equals 4 times x to the 5 minus 5 times x to the 4 plus 1. As explained earlier, in this case, there are two complex conjugate zeros. We assume they are a plus bi and a minus bi here. Apart from that, it also has alpha and 1 double zero at x equals 1. So according to the relations between the polynomial zeros and its coefficients we discussed earlier, the product of all the zeros equals 1 over 4. After simplifying, we have a squared plus b squared equals -1 over 4 alpha. Since alpha is in the range of -1 and -half, including the point of -half, we deduce that the modulus of the complex zero is between half and 1 over square root 2, including the point of 1 over square root 2. Hence, we have proved all the zeros of the polynomial has modulus less than or equal to 1. Example 2 shows the monic polynomial of nth degree with n as its maximum absolute coefficient, and beta is the root of this polynomial pz. There are two questions in this example. The first one is to show that the modulus of beta is less than or equal to m, while the second question is to prove that the modulus of any root is less than 1 plus m. As for the first question, since beta is the root of the polynomial pz, here x is replaced by beta, so we have beta to the n equals negative a sub of n minus 1 beta to the power of n minus 1 minus a sub of n minus 2 beta to the power of n minus 2, then minus all the way up to minus a sub 1 beta minus a sub 0. Based on the principle of the modulus of the sum of all the terms is less than or equal to the sum of the modulus of all the terms, and according to the definition of m, we have the modulus of beta to the n is less than or equal to the m multiplies the sum of the modulus of beta to the power of n minus 1 and the modulus of beta to the power of n minus 2 and all the way up to modulus beta n1. Here we continue with question 2 of example 2. Since the sum of the modulus of beta to the power of n minus 1 and the modulus beta to the power of n minus 2 and all the way up to the modulus of beta n1 equals the result of the modulus of beta to the power of n minus 1 over the result of the modulus of beta minus 1. The inequality of m divided by the result of the modulus of beta minus 1 is greater than 1 is obtained. If the modulus of beta minus 1 is greater than 0, then the modulus of beta is less than m plus 1. When the modulus of beta is between 0 and 1, since m is greater than 0, the modulus of beta is less than m plus 1. If the modulus of beta equals 1, then the modulus of beta is less than m plus 1, since m is greater than 0. In summary, for any root of the polynomial pz, the modulus of beta is less than m plus 1. Example 3 shows a quadratic polynomial pz with a real parameter k, assuming alpha equals x plus yi, where x and y are real numbers. If alpha and alpha I are zeros of the quadratic polynomial pz, and the conjugate of alpha is not equal to alpha I, there are 6 questions in example 2. The first question is to explain why the conjugate of alpha and negative alpha I are zeros of the quadratic polynomial pz. The second question is to show the quadratic polynomial pz is equal to z squared multiplies z minus k, or in parentheses squared, plus kz minus 1, or in parentheses squared. The third question is to show that the quadratic polynomial pz is equal to either z squared plus 1, or in parentheses times z plus 1, or in parentheses squared, or z squared plus 1, or in parentheses times z minus 1, or in parentheses squared, given that the quadratic polynomial pz has a real 0. The next question is to show that all the zeros of the quadratic polynomial pz have the modulus value of 1. The fifth question is to show that the k is equal to x minus y. Hence, the last question is to show the value of k is between negative square root 2 and square root 2. Let's start with the first question. Since both alpha and alpha I are zeros of the quadratic polynomial pz, and k is a real number, according to the conjugate zero theorem, the conjugate of a complex zero also is a zero of the polynomial. As it can be seen that the negative alpha I equals negative y minus xi, which is a conjugate of alpha I. So both conjugate of alpha and the negative alpha I are also zeros of the quadratic polynomial pz. Here we continue with question 2 of example 3. In order to factorize the polynomial pz, we separate the quadratic term of 2k squared z squared to k squared z squared plus k squared z squared, as shown in red color here. Then we put the first 3 terms in a parenthesis and the last 3 terms in another parenthesis. It is actually not difficult to observe that after taking out the common factor z squared in the first parenthesis, the remaining terms just form a complete square, while the terms in the second parenthesis also form a complete square. Hence, we have shown the required expression of the quadratic polynomial pz, which equals z squared multiplies z minus k, or in parentheses squared, plus kz minus 1, or in parentheses squared. As for question 3, if the quadratic polynomial pz has a real zero, then based on the expression being deduced in question 2, in order to make the polynomial pz equals 0, both z minus k and kz minus 1 must be 0. So the values of the real 0 and k are found by solving the two simultaneous equations. The real 0 is equal to k, which equals 1 or negative 1. After back substituting the values of k, which is 1 or negative 1, into the variable of the polynomial pz, we factorize the pz accordingly and obtain the required expression. When k equals 1, pz equals z minus 1, or in parentheses squared, multiplies z squared plus 1, or in parentheses. When k equals negative 1, pz equals z plus 1, or in parentheses squared, multiplies z squared plus 1, or in parentheses. To solve question 4, we need to recall the relations between the polynomial zeros and its coefficients. So the product of all the complex zeros equals the constant of the quadratic polynomial pz, which is 1. After doing some expansion, the left-hand side of the equation equals x squared plus y squared, or in parentheses squared, equals 1, which implies that the modulus of all the zeros of the quadratic polynomial pz equals 1. As for question 5, since the sum of all the zeros of the quadratic polynomial pz equals the negative cubic coefficient, which is 2k, so after adding up all the zeros, we have the simplified equation of 2x minus 2y equals 2k. Therefore, we have shown that k equals x minus y as required. Here we continue with question 6 of example 3. In order to find out the value range of k, which equals x minus y, since we know all the zeros of the polynomial pz are evenly distributed on a unit circle in the complex plane, we have simultaneous equations such as k equals x minus y and x squared plus y squared equals 1. After substituting y from the first equation to the second equation, we can express k in terms of x. Then we differentiate k with respect to x and find that the maximum and minimum values of k can be obtained at x equals square root 2 over 2 or negative square root 2 over 2. Hence, we find the value range of k, which is between negative square root 2 over 2 and square root 2 over 2, including both endpoints. Alternatively, since the modulus of all the zeros of the quadratic polynomial pz equals 1, we may assume that x equals cosine theta and y equals sine theta. So k equals x minus y can be expressed as cosine theta minus sine theta. Hence, we may express cosine theta minus sine theta as a single sine function by multiplying an appropriate constant. Here is square root 2 as displayed on the screen. Hence, k can be expressed as square root 2 times sine pi over 4 minus theta, or in parentheses. Therefore, the value range of k is between negative square root 2 over 2 and square root 2 over 2, including both endpoints. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.